One of the things we've noticed is that if we have, for example, a Wheatstone bridge circuit like this one, this measured voltage that we get out is going to be small. It's going to be on the order of millivolts. So this measured voltage might go from, in millivolts, -3 up to about +3. Because it's a bridge, it can go either positive or negative, the difference between these two voltages, VA and VB. So this is a differential output. So the absolute voltage here is about halfway in between 5 volts and 0. It's about 2.5 volts. And one of these will be a little bit bigger or a little bit smaller than the other one. So it's a voltage difference. Now, at the other end, we'd like to be able to record what's going on our Arduino. And it doesn't do differential voltages. It only does absolute voltages from 0 up to 5 volts. So we can't read a negative voltage with it. And on the 0 to 5 volt range, we'd have a really hard time even seeing these changes that are in the millivolt level, 1,000 times smaller. So somehow we need to take this signal that we might read from the bridge that could look something like this, that ranges over a relatively small range, and we need to make it bigger and still retain the same shape so that we can read it on the Arduino. So we'd like to wind up with something like this. And unlike over here, we can't do differential, so we'd like to wind up with all of our signal being above 0 volts. So the scale over here is going to be in volts, and we'd like the maximum to wind up being less than 5 so that it fits within that range. So that's what we'd like. That's what we need to be able to do, is to translate this really low voltage signal that goes positive and negative into a higher voltage signal that the Arduino can read, can see, and that all stays above 0 and 5. Now, to do that, we'll use a black box. We'll call it an amplifier. And that amplifier has to do two things for us. It has to increase the signal to make it bigger in magnitude, instead of being millivolt sized, to make it volt sized. And that's referred to as the gain of the amplifier. That's a multiplier by which it increases the voltage. But in addition, we need to get this from negative up to positive, so we also want an amplifier that can provide an offset for us. And in the amplifiers we'll use later, we'll get that by using a pseudo ground setup, but that's going to come later when we talk about the actual box for that amplifier. So somehow we need to find a black box that fits in the middle here that'll take that differential input and turn it into an output voltage that's got the characteristics that we want. And we'll talk about the output voltage as being equal to the input voltage, the measured voltage, times the gain. So that'll take this small voltage here and make it into this much larger voltage difference here. And we also need an offset. That's going to take this value for the 0 crossing there. That corresponds to this point here. And that's the idea of the offset. So plus some offset P. So a gain of G and an offset of P to push the voltage up. And that's what we'd like to get from our amplification. Now we're going to go and look a little later on to find out how we actually get that from an instrumentation amplifier, which is an INA 125 is the part that we're going to use in our labs. So this need for amplification, you'll run into it over and over again, because very often from bridge circuits, which are measuring resistance, or from thermocouple circuits, or from any number of other small signal devices, we'll need to take that small signal and turn it into a larger signal in order to be able to read it with our analog to digital conversion.